Let's compare the pi model and the T model from each other so we can do an AC analysis on a single stage common emitter amplifier with RE not bypassed. So let's start that. Let's put a single stage amplifier, common emitter with RE not bypassed. In other words, we're coming out also from here, and this would be our expected AC output, this being RC, circuit being fed by a positive DC source, typical voltage divider, input resistance feeder to control the voltage level at the base, this being the collector, this being the emitter, and an abstraction of an AC source, small signal, to this common emitter single stage. And this would be our VN. Okay, so VN, again, is considered in AC from this point to this point. Okay, so from ground to the base. So now, again, we want to know, how does the pi model look like and the T model look like? Okay, so let's start with the pi model. And remember, this time, we will consider RE unbypassed. Let's start from the left all the way up to the right. So let's redraw our power source, or the feeder signal. This capacitor here will be considered a short at a certain frequency and capacitance value, where X of C here is almost 0, at the operating frequency that you want this stage to work. Let's not forget R1 here and R2. Okay, so what does that mean? R1 and R2 also, since in AC, VCC will be considered your reference ground, will be in parallel. So we would have R1 here. We would have R2 here. And now, remember, this is still the base. But we have a resistance from base to emitter. But for the pi model, it is specifically expressed. And let me just put the emitter here now. And I will handle this in a minute. So what happens from the emitter to ground? Well, we have big RE. Right? So this would be big RE, the same as this one. Now let's get back to our pi model representation of this internal resistance. This would be beta RE prime, as we've seen in previous models that we've drawn before for the pi model. But specifically now the difference is that we have RE from emitter to ground. So what else? Well, we still have our current generator. And this current generator here will be beta little IB, assuming we have little IB going through the base, okay? Which is exactly the same current, so let me just draw it here as IC, since IC is equal to beta IB. Some assumptions we can take. We've seen in the hybrid model that we have an admittance here, HOE, that is in parallel with this current source, which means RO, which is equal to 1 over HOE, we will assume that it is very big, right? So we'll assume almost like it's infinity. So we won't draw it here, so let me just erase it. So no need for that. And it will be between the collector and the emitter, by the way. So that means if the collector is here and the emitter, that resistance will be from here to here, not from here to ground. So we have to be really careful. Now, what do we see from the collector right here to this virtual ground? Well, we see RC. Let's go ahead and draw RC. And that goes to ground. This point here is the same as this one. And V out would be sampled from this stage, or at this level. This would be V in. Okay, how about the T model? Okay, so this was the pi model, and now we're going to look at the T model. Same thing, we have a source, V in, R1 in parallel with R2. Now, in a lot of publications, you might see RB representing these two in parallel as one resistor. Okay, so don't panic if you see that. And for the T model, however, I'm just going to go draw a line here and put, let me do it this way, actually. Let me do it this way. Put little RE here, and however, this would be the emitter, but we will put RE here, ground, but we're going to connect our current source right here. Still, beta IB, assuming little IB is here, assuming this is the base, right? This is right here, still the collector at this point, okay? So from here down, we would have RC to ground. And again, V out sampled right here. Okay. So what value we put here? We'll put little RE prime. Now, what is little RE prime? Little RE prime, after we do a DC analysis, is approximately equal to 25 millivolt divided by IEQ, which means at quiescent point IE. Now, what's the advantage of using this model versus this model? This model actually makes it really easy to figure out AV, even this one, but much easier with this one. However, this one has an advantage where we can right away calculate Rn, or the input impedance of this circuit as seen from here. Because if you look at it, what you have is these two in series in parallel with R1 and R2, which makes it really easy to visualize. Okay? Why? Because I can move this line here, right here, virtually, back to the base. And this here is just simply a current node. And the current that you have here is IE, assuming, and again, it's a model, because it will be the same current IE going through RE. Okay? However, the important thing is that these two series will be in series. Both of them, as an equivalent resistance, will be in parallel with these two. Hence, Rn will be all these three resistors in parallel. When I say three, the third one being these two together in series. Makes it really easy for the analysis, again, of Rn. This one here, not so obvious. You have to be really careful. Okay? Because the split is done right here, right? So we have to be really careful figuring out Rn from this angle once you lift up, or you do not use a capacitor to bypass Re. So things can be a little different here. Just keep that in mind. Okay? Excellent. So later on, in our next video, we will do a full analysis either using this or this, depending on our needs and what's the advantage of one versus the other. We'll take that advantage into consideration when we're doing our analysis for input impedance, output impedance, amplification factor like AV, or current amplification as well, and power amplification. We'll see you for the next video.